Good evening, ladies and gentlemen. Welcome to the Space Telescope Science Institute for a very special evening. We are so excited that we are able to partner with another great Baltimore institution, the Baltimore Museum of Art, tonight. My name is Dr. Frank Summers of the Office of Public Outreach here at Space Telescope, and usually I am your host for these public lecture series evenings, but we are going to turn it over to the Baltimore Museum of Art to handle the show tonight, because we, of course, have our very, very special guest, Dario Robleto, whose installation is at the Baltimore Museum of Art. And so let me, first of all, say thank you for this wonderful partnership that is enabled tonight, and I hope it's the beginning of a beautiful friendship. Ladies and gentlemen, our host for this evening, Kristen Howman.
So the job of a good host is to get out of the way and let everyone have a good conversation, and that's what I want to do. But I do want to give you a little information and also say how happy we at the Baltimore Museum of Art are to be part of this evening, and as I understand it, part of the inaugural Science and Art thread for STScI's Tuesday Night Lecture Series. And this year marks the Hubble's 25th anniversary. It also marks the culmination of the BMA's 100th anniversary. So we're happy to all join in the celebration together. Before I introduce our speakers, I'd like to offer a special note of gratitude to two people. The first is Zsolt Levay, who is the imaging group lead here, and also Rachel Rabinowitz, who is a member of our Friends of Modern and Contemporary Art group at the BMA. Without Zsolt and Rachel, we wouldn't have made the connection between the two programs, and we're really happy that this has come about, and so thank you. I should explain that the Friends of Modern and Contemporary Art at the BMA is technically the co-host or co-sponsor of tonight's program. And if you do get inspired by what you hear tonight, we'd be happy to tell you more about that Friends group. There's information on the BMA website. Now, just a few business items. We encourage everyone to come to the museum to see Dario's show, which runs through March 29th. And again, if you are sort of tantalized by what you hear tonight, there'll be another opportunity to hear from Dario this Saturday at 2 p.m. in the museum's Big Table space, which is a very innovative educational space within our contemporary wing, where Dario will be collaborating with a locally based sound artist, Tim Noe, to do both a demonstration and a hands-on activity. So it'll be really literally sitting across from an artist across a table rather than in an auditorium, and I hope you'll take advantage of that more intimate space and experience. The format for tonight will be first a presentation by Dario, and then that will be followed by a response from Frank. Then we'll open up the whole floor to questions, both from the audience that's here, but also to the people who are listening in and watching us via live stream. So those folks out there in cyberspace can both send questions in via YouTube and Twitter. The hashtags are Hubble25 and ArtBMA. That's ARTBMA. And now, without further ado, I'm pleased to welcome Dario Robleto, who is an artist based in Houston, or to use his own, I think, more evocative description, a materialist poet. And indeed, that's an apt way of describing what Dario does. He transforms materials as diverse as vinyl records and black swan vertebrae, sea urchin teeth, into incredibly intricate sculptures, which you can see at the museum now. He also creates work on paper and does innovative spoken performances that combine research and storytelling. Rigorous investigations into historical and scientific topics inform all of that work. The 2004 Whitney Biennial, although not the first, was certainly an important high-profile exhibition of Dario's work that introduced it to a wide audience. And since that time, Robleto has both widely exhibited his work and had his art collected by numerous institutions. Over just the past few years, he has had solo shows at Houston's Menil Collection, the New Orleans Museum of Art, the Des Moines Art Center, and Denver's Museum of Contemporary Art. Among the awards he has received are research fellowships at the Smithsonian's National Museum of American History and Rice University. Robleto has also been an artist in residence at the University of Houston and the Headland Center for the Arts in Sausalito. His work has been covered not only by major art publications, but has also been featured in the pages of the New York Times Science section. As many of you already know, I feel you might not need an introduction, but I'm going to do one anyway for those in the audience that come via the museum. Dr. Frank Summers' expertise spans a diverse range from research, cosmology, and high-performance computing to scientific visualization, education, and public engagement. For the last 14 years, he has contributed to all aspects of the Hubble and James Webb Space Telescope press, education, and outreach through news media, websites, educational programs, social media, museums, and planetariums. His specialty is creating scientific visualizations by combining research computer simulations and Hollywood rendering techniques. He was a writer, science advisor, and scientific visualization supervisor on the IMAX film Hubble 3D, contributed data science and visuals to the Academy Award-nominated IMAX film Cosmic Voyage, and directed the IMAX short film Hubble, Galaxies Across Space and Time. Online, you can hear him as the host of the Hubble's Universe Unfiltered, which is a video podcast and blog, and he lectures widely, consults on books and documentaries, and has created a 24-lecture DVD course on new views of the solar system. Dr. Summers obtained his BS in physics at Virginia Tech and his MA and PhD in astronomy at the University of California at Berkeley. After research postdocs at Princeton and Columbia, he has shifted his focus to professional astronomy outreach as the lead astronomer developing exhibits for the Hayden Planetarium in New York City. And now we are fortunate to have him in Baltimore in the Space Telescope Science Institute's Office of Public Outreach. So please help me welcome to the stage first Dario.
So I just want to begin tonight with my own thank you. It's not every day that an artist or anyone really gets to address the people or institution who have been so crucial in forming their very worldview. And as we celebrate 25 years of Hubble's endeavors, I want to say thank you to all the scientists and administrators who've ever worked here and keep this incredible device functioning and breaking new ground. It is and will surely continue to be remembered as one of our greatest scientific achievements. But the part I'm probably more qualified to thank you for is that it will equally be remembered as for its inspiration on the artistic imagination. And you will not find a bigger advocate of why the arts and the sciences should continue to be in conversation together and help push our fields forward, but also to remind ourselves that we are both part of a long lineage. We share a tradition of rigorous observation, endless questioning and experimentation, and all, of course, at the service of our thirst for meaning and wonder. And we live in an era of such specialization of knowledge that on paper it seems odd to ask, what could the search for dark matter or the planets on the atmosphere on exoplanets or the study of supernova, what could it possibly have to do with contemporary art? But in my opinion, this is just an illusion of the fragmentation of our time. And we can and should, of course, come to wildly different conclusions. But I just don't want us to ever forget that it is fearless questioning, which is the seed we both originate from. Which is why I'm thrilled to be here. I hope that's obvious, and can bring three institutes together that I hold very in high esteem: the Hubble, the Baltimore Museum of Art, and MICA, school I have the pleasure of teaching at this week. And just remember that we all come from the same seed. So science is a crucial part of my life, but it was ultimately art that allowed me the flexibility and play that I desperately needed. And so for me, the word artist is really just this umbrella term for all of my passions to just creatively entangle under. And my practice can really take any form I choose it to. And sometimes that means an object or a drawing, or as Kristen said, I like to call myself a materialist poet. Some days I feel like I'm just a good detective or a sound archaeologist or a researcher, which tonight I hope we'll emphasize, and also just a good storyteller. So with that in mind, I wanted to share a small excerpt of where my latest research is headed. And so I've been working for the past several years on a book and accompanying sound works with my colleague, his name's Patrick Feaster, who I'll speak to in more in a minute. And that I hope this will illustrate some of these unexpected roads I think that can be followed when art and science are in dialogue together. And the Hubble has had a very deep impact on this project and all my work really in two big picture ways. And one of it are two things that I would argue that the Hubble shares in common with art, which is its ability to envision the invisible and its meditation on time, something I spend a lot of time thinking about. And I think few things summarize those aspects better than, of course, Hubble's deep field images that they've routinely released over the years, and the incredible ingenuity it has shown in how it captures light that would have remained invisible to us, and in the process has completely revolutionized our expectations about how we access the distant past. These two things have had a deep influence on another passion of mine, which is the history of recorded sound, and which I'll also speak to in a second. So with the spirit of Hubble as our backdrop, I wanted to just metaphorically turn it around back at us. And the first human who walks under its gaze, if we could imagine it using its power of envisioning the invisible and deepening our access to the past, and have it focus on something as mysterious as the most ancient stars, which is the human heart. And it can strike a modern viewer as odd today, but for most of recorded history, the idea of looking at or touching or understanding the movements of a beating human heart seemed as distant and far away as the edge of the solar system or the dark side of the moon. So with that in mind, I'd like to suggest an idea that it's maybe quite obvious, but again, I think it can lead us somewhere unexpected. And it's this, which is the vast majority of heartbeats that have ever beaten on this planet are gone. And I don't just mean the lives they soundtracked, but the beat itself as its own sensory memory. The average human heart, as you may know, beats close to 2.5 billion times in a lifetime. And when you consider the tens of billions of people who have ever lived on this planet, you quickly get a sense of how vast this auditory experience has been. But heartbeats, like all sound waves, are ephemeral and fleeting by nature, and within an instant after their birth, they have already begun to dissipate and as they absorb into your inner chest wall and completely vanish. And unless a passing ear or stethoscope was placed on your chest, the sensory memory of this transitory moment is forever gone. And our hearts themselves have certainly moved on, only concerned with the next beat. The idea that the heart would be nostalgic for the musicality it had just accomplished is not possible. Life insists the heart must keep moving forward. But this pure functionality of the heart and the fleetingness of its beat is in tension with the deep human longing to reflect on and find meaning within what our hearts have just accomplished. And history is filled with contemplation and attempts to preserve knowledge of the heart. And one could easily argue that much of religious, artistic, and medical history has been propelled around matters of the heart. So to reflect on the nature of the heart's intentions, whether as a metaphor or its physiology, is to reflect on the nature of life itself. And our major forms of knowledge, like art, religion, and science, have found incredibly inventive ways to document this quest and share it through time. But even with this wealth of creative and medical knowledge, what's largely remained unexplored has been the history of the audible experience of the heartbeat. And the reason the majority of heartbeats have forever vanished is that so few have ever been audibly recorded unanchored as singular moments in time for the very simple reason that we just have not known how to record them for most of recorded history. So if the heart as a contemplative object is the most vital symbol to the artist, the physical embodiment of the soul for the religious, and a majestic feat of engineering for science, then what about its sound? And because of the vessel producing it, the heartbeat is perhaps the most richly significant sound that has ever been created, and yet I think most of us would be hard-pressed to talk about its history. So what do we draw from to tell a history of the sound of the human heartbeat, given this vast absence of historical sound recordings? And what could a past, present, and future of the heartbeat possibly mean? So for me, the artistic desire to trace this history started with this question. How did the sound recording of the electrical signatures of a human heartbeat and brain waves in love end up headed for the other side of the solar system? It is from years of asking this unlikely question that I became convinced there was still an unknown history of the human heartbeat waiting to be explored. And although I'm now able to ask this question more clearly to myself, it's only because of my decades-long persistence in trying to make sense of an early childhood memory. And when I was about 7 years old, I'll never forget the day I had stayed home sick from school, and by complete coincidence, I happened to catch on TV that NASA was releasing a 1-800 number to the public, that the public could call in and hear something that they were describing as sounds sent to space, or some sounds of space, that they had launched on a probe that was heading past Saturn and Jupiter. And this is the same year Star Wars was released, and so in the age of Star Wars and an active imagination and the still cloudy head of a cold, my young mind raced with the possibilities of what this could mean. I wondered, did they mean we had received our first alien communication? Or had we invented some new type of laser? Whatever it was, I had to know what this sounded like. And I remember immediately calling my mother. I told her the whole story in great detail. Details I know had snowballed beyond plausibility at that point, and asked her if I could call this number. In her confusion about what in the world I was talking about, she told me no, I had to wait till she got home. And I know when I mentioned 1-800 numbers and aliens, she got very worried. And so what turned out to be quite an agonizing day, I waited for her to get home. And even though I was still quite ill, as soon as I heard her drive up, I met her at the back door. As soon as she opened the door, I reached out for her hand, placed any other thing. Here's what in the grooves of a gold record. And in 1977, NASA launched what it called its grand tour of Voyagers 1 and Voyager 2. And their goal was to explore the outer planets of the solar system. And once completed with this grand tour, the Voyagers would be in the incredibly rare position to actually exit the solar system by breaking free of the gravitational pull of the sun, a very rare phenomenon. So realizing the symbolism, rarity, and even poetics of such an occasion, astronomer Carl Sagan was asked by NASA to lead a team to design an interstellar message to be placed on board as an act of goodwill greetings, just in case anything ever were to happen upon it. But on a more poetic level, it was a scientific attempt to build an ark that would potentially be our planet's last remnant of our existence. And the goal was 1 billion years, and the medium was a gold-plated copper LP record, what has now very famously come to be known as the Golden Record. And embedded in its grooves is a small group of scientists, writers, and artists, humble but noble attempts to account for the vast complexity of Earth's history through things like language, images, music, and sounds of the natural world, and all in the roughly 2-hour space limitations of 2 sides of a record. It is the greatest mixtape ever assembled, the greatest DJ set ever spun. And among the gems the team included is, for me, I would argue, the most poignant recording of all, which are the compressed brainwaves and heartbeat recordings of a 27-year-old woman who had just fallen in love. And in a moment of real creativity and vision, Anne Drean, the creative director of the record, who only a few days before had secretly professed her love to Sagan, and he to her, and got engaged in the same conversation, she had the imagination to wonder if an advanced future intelligence could somehow take the audible recordings of the electrical signatures of her heart and her mind and decipher the meaning of a human thought. This was really starting to move into the realm of the poetic and the speculative rather than the strictly scientific. But it's one of the beauties of this project is that I think it's a real testament to the team. They decided it was worth a shot. An optimism in the face of uncertainty that really defined the whole endeavor. So with the deadline to turn in their selections fast approaching, Anne made an appointment at the hospital to be hooked up to an EEG and an EKG machine to record her innermost thoughts. So with the weight of being potentially the last human thought, one that would quietly wander 1 billion years in the darkness of interstellar space, Anne rose to the occasion and intertwined with the dutiful world historical facts anybody would feel called upon to remember in such an occasion. She also could not help but to reflect on falling in love just 2 days earlier. So in the astronomically remote chance the Voyagers ever found, there will remain the further astronomically remote chance such an abstraction as the concept of human love as electricity converted to sound can be deciphered. And it's really staggering to reflect on what's writing on these few seconds of sound. And I want to play the recording of her compressed heartbeats and brainwaves that made it on board, waiting to one day be played again, and which had so confused and disappointed me as a 7-year-old. So on September 13th of 2013, the front page of the New York Times read, "Exiting the solar system and fulfilling a dream. NASA craft aloft 36 years enters region between the stars." And there it was, a human mind and heartbeat and love, lunging toward an afterlife in a region of time and space that no art or religion had ever accounted for. And just to think for a moment what this means for Anne. On board, this moment in her heart and mind no longer follows the rules that all bodies must. They don't even follow the rules of our most ancient documents or monuments. 1 billion years will easily surpass the life of the planet that holds them. Like a theorist of love's memory, Anne has been given the chance to test one of our oldest and most anxious of questions. Does love survive the death of cells? And one can imagine that once the Voyagers set sail with the Golden Record, part of the story had gone into an epically long pause. And not the Voyagers themselves, of course, which have revealed incredible, groundbreaking discoveries, but at least the part of the story where we wonder if the Golden Record will ever make it to somewhere, to something, to some type of consciousness that's evolved in just such a way that sight, hearing, curiosity, abstract reasoning, and who knows what else, provokes them to give the record a spin, and like a roulette wheel, chance continues its poetic work of preserving and communicating the abstraction of human love. It's a beautiful, timeless story, and as much as we can admire the romance behind it, the story doesn't have to end in our imaginations as a wondrous what-if scenario. In my mind, what Anne did was an artistic challenge for us, for the present. And just as we hope some consciousness will one day ponder the strange sounds and symbols inscribed in this modest disc of gold, I think the creative minds of today should also be considering, speculating, and debating this vessel and its contents as we would any hieroglyph of our ancient past. Anne's inspired gesture opened a new window to contemplation, about the heart, the mind, and sound. And so by reflecting on Anne's heartbeat as emissary, as a significant moment in the audible history of the heartbeat, interesting questions can emerge. For example, who, where, and when was the first human heartbeat ever recorded? What technology would have been needed to do this? This moment had to have occurred to set the chain of events in motion for Anne's inspired recording. Is there a forgotten history of the act of one partner listening for the other's heartbeat, hoping to find meaning within it? Almost instinctually, we talk of our hearts and minds as embodying our emotions, but do we really mean it? Are our emotions really in there? And if so, is it truly possible to record such a thing and expect for it to be played back like we would our favorite song? And as Anne's heartbeat arrives at its unfathomable destination, can we assume our own heartbeats are still going to sound the same? Anne is pushing what we can expect from a recording to its absolute limits. So because Anne's story is so singular and it's inspiring, it has inspired my own research to try and tell the history of the human quest to record our hearts and minds, to try to link the chain of events which had to fall in place and which would culminate, I think, on her day in 1977, when so much was riding on what was embedded in her recording. And I've wanted to tell that history through sound, but because so little of the early history of the human heartbeat has been audibly recorded, it would seem that to tell the story through sound would be this insurmountable problem. But recent creative breakthroughs by researchers in 2008 have allowed for an ingenious workaround to this problem. So just as Anne's heart, just as Anne's gesture raised the expectations of what we can expect from a sound recording, these researchers' groundbreaking insights required a complete rethinking and creative expansion of our current understanding of what constitutes a sound recording. And I would argue this is where really interesting parallels with Hubble start to take shape in the ingenuity in how we access the past. So prior to Thomas Edison's game-changing invention of sound recording and playback technology in 1877, the ephemerality of sound meant that it lived and died in the moment of its creation. To record sound before this time meant it appeared as oral or written descriptions or musical scores, never as a repeatable, live, real-time moment we would all associate sound recording with today. And so for this reason, 1877 has always been the absolute limit as far as accessing our recorded sound history, as opposed to what I showed a while ago, Hubble's now at 13.2 billion years with light. So a general consensus of the definition of sound would be something along the lines of this: a record made by documenting sound waves over time in order to reproduce them automatically as sound. But there was another option of what we mean by sound recording in the pre-Edison era that had not been considered as a sound recording in this traditional sense for two important reasons. One of them was that the creator of the recording made it without the intention of ever playing it back. And two, the goal was to represent and study sound visually, not audibly. The inventor of this type of machine recording was a Frenchman named Edward Leon Scott de Martinville, who was the first to build a device in 1857, the phonautograph, that could record aerial sound waves over time. And inspired by the mechanics of the human ears, he reasoned that funneling sound waves onto a membrane similar to the eardrum should produce vibrations that could be registered with the aid of an attached stylus to the membrane. And these vibrations from the stylus would have been traced into a blackened, soot-covered piece of paper that was being manually pulled under the stylus tip. So Scott was partly driven in this quest to find a way to preserve the subtleties, the expression, and most importantly for my talk tonight, the emotional content that forms the individuality of speech, singing, and musical playing. His phonautograms were meant to capture these expressionistic qualities and would be visually represented in the variations of the wave tracings. And to him, there was emotional meaning literally in the waveform. And he called this a new form of natural writing or living speech. But in Scott's time, it would have been up to a future audience to learn this new visual language of waveforms to unlock the emotional nuances of a past audible event. But this would still be a process of visual reading, only played back in the sense of how you'd play a song in your mind's ear. And for a number of reasons, Scott's hope for the phonograph never took hold in the way he had intended. But 151 years later, in 2008, his hope for the preservation of expression in sound waves, this idea of living speech, was finally given that chance to live when sound archaeologist Patrick Feaster and sound historian David Giovannoni suggested and stunningly demonstrated that these visual sound tracings, made before the conceptual notion of playing sound back had even been invented, could in fact be played today as sound. So after forming what they called the First Sounds Collaborative, it was a team of researchers devoted to finding the oldest sounds on the planet and making them available to the public. They located Scott's tracings that, thank goodness, he had wrapped up 150 years earlier and had deposited them in an archive in Paris. And they took incredibly high-resolution scans of these soot tracings. And after much graphic processing work and very inventive magnification techniques at Lawrence Berkeley National Laboratory, the team was able to digitally play back the tiny embedded waveform images magnified from the scans with what they called a virtual stylus. They never even had to touch the soot. They just scanned it. And were able to track them with a stylus in the way a vinyl record would be played on an actual record player. And in 2008, they debuted to the world a recording of Leon Scott singing the French 18th century folk song, Au clair de la lune, in his laboratory in 1860, 17 years before Edison has even thought about playback technology and as the Civil War would have been beginning. Here's a sample of what they resurrected. This is science fiction made real. As the idea of audio archaeology or prehistoric sound has long fascinated thinkers, but no one's ever been able to prove this, which is what makes this team's discovery so remarkable. And like the Hubble, I think it's always a startling achievement anytime new pathways to the past are opened up in ways nobody expected. So Feaster has since gone on to refine this playback process and develop several other approaches which we're using now in our project. And I won't go into here, but if you're interested, I can't recommend his book enough, which lays out the technical side of this in much greater detail. It's an incredible book of artistry as much as science, in my opinion. So by challenging the definition and assumptions of what constitutes a sound recording, what Feaster refers to as eduction, and I love this word, paleospectrophony, not only gave us access to the earliest recorded human voice, but it now allowed the consideration of resurrecting the other defining audible experiences of our identities, which is the sound of our hearts and our pulse. In a really fascinating cross-pollination of disciplines, it was the same concept of trying to visualize sound that the early physiologists and cardiologists turned to when they were confronted with the biggest dilemma in their own field, which was this question: how does one record and visualize the interior movements of the heart? But because we're dealing with the heart, the desire to probe, study, and record it was a much more sensitive gesture than trying to record anything else. And I wanted to just take a quick moment to illustrate a few key points that can help us understand why the quest to record the heartbeat was such a highly charged endeavor. And it will seem hard, again, for a modern mind to believe today, but in these earliest recordings of the heart and the pulse are ancient narratives and cultural tensions about the location and the materiality of the soul and the supposed absolute limit of scientific knowledge. And at the very beginning of recorded history, curiosity about the heart and the pulse is everywhere to be seen. The first attempt to lay out a systematic explanation of the heart's movements is likely contained in the Ebers Papyrus from 3,500 years ago. But across the globe, the most ancient texts from the majority of cultures speak of grappling with what the heart and the pulse sounds could mean. So with this innate curiosity about the inner workings of the heart, two things have consistently stood out across time and cultures. One is this: mystical and religious traditions that held the heart as the literal conduit or vessel of the immaterial soul. And two, this deep fear of physically engaging with the heart directly. It seems all ages have simultaneously revered and were horrified by what those inner chambers were doing, because nowhere did the spiritual and the physical intertwine so completely than at the site of the heart. And for the most part, this was driven by a belief in an afterlife and the potential resurrection of the body in that new existence. So a well-known example you may be aware of are the Egyptians who, for example, always left the heart inside the mummified corpse because of their belief that the heart was physically needed in the afterlife. So removing the heart for the sake of knowledge over its potential need in the afterlife has, for most of recorded history, been a taboo of the highest order. And this mixture of fear and reverence severely stunted consistent breakthroughs in the study of the heart. And because the heart was believed to be a literal vessel of the soul, this attitude also suggested we could never know how the heart truly works, because it was operating under rules outside the domain of science. And it wasn't until the Renaissance in the 14th to 17th centuries that the taboos on human dissection slowly were lifted and a series of investigations on the heart began, but this was still very crucially only occurring on dead hearts. It's important to note that even in this investigation, it was still motivated by the search for the physical location of the soul in the body. It was René Descartes in the 17th century who finally took the major steps forward to open the heart to modern scientific exploration. And his radical move was to argue that the site of the soul was in the pineal gland in the brain and not the heart. He was still unwilling, though, to completely eliminate the soul's physical presence. So not only did he rearrange this heart-soul-mind interaction that had been in place for centuries, he also greatly lowered the physical responsibilities of the soul. And how this relates to the heartbeat is that, for example, the soul was no longer needed to explain the movements of the heart, and hence the heartbeat. So with this new philosophical framework, breakthroughs and revisions of the physical understanding of the heart occurred at a pretty rapid rate. And these breakthroughs had much to do with the fact that for the first time, scientific devices were being applied to the study of the heart as religious and cultural taboos softened. But even with the invention of the stethoscope in 1816, one of the most transformative medical devices ever invented, and which opened up a new sonic landscape of the heart, by the middle of the 19th century, there was discussion that we had hit a natural limit of knowledge about the heart and the heartbeat, and there was no foreseeable way around this problem. So on a surgical level, nobody could see around the problem of how do you operate on a still beating heart. And then on a diagnostic level, the stethoscope would always have a weakness, because unless one could standardize these recordings, this knowledge would always be susceptible to subjective interpretations and just the decayable workings of human memory in general. So by 1853, the major obstacle to understanding the heart remained consistent. If you can't access a beating heart, either because of cultural or religious taboos, or because the devices of the era were not up to the challenge, then how do you record its actions indirectly? And the difficulty in this era of measuring and recording the inner workings of the heart and pulse can't be overstated. These movements of the heart and pulse are incredibly low energy and occurring in fractions of seconds, well beyond the ability of the unaided human senses to understand in great detail or store to memory. An instrument would have to be designed to try and capture these movements without interfering or altering them, and convert them into a visible form that could then be permanently written on a medium. So after centuries of erratic advancements, a turning point occurred in 1853, when the German scientist Karl von Fjord introduced his sphygmograph, or pulse writer. This was the first to give visual tracing on paper and the taboos of around. Pulse waves with the most perfect sharpness and without action. This is what we're seeing little. He could not find a medium delicate enough to hold the image. Fjord turned to the most delicate things he could find, a single human hair and soot from a candle flame. So in this beautifully coincidental moment of history, the practicalities of science accidentally produced a poetic moment of breathtaking fragility, the first visual evidence of the now near universal sign of life, the pulse curve, was traced for the first time in 1853 by a single human hair and the residue of a flame that burned and extinguished 162 years ago. In the most unexpectedly delicate way, Fjord had opened up a radical new avenue to visualize the activities of the heart through the pulse, and hence life and death. It's truly a wondrous blending of the scientific and the poetic, and these pulse pictures made the invisible visible and began to build a narrative of the heart with unforeseen clinical, physiological, and I think most thought-provokingly as an artist, philosophical, artistic, and religious implications. So Fjord tapped into an ancient, fundamental human yearning to know oneself through the workings of their own heart. Then only a few months after his own first pulse self-portrait, he made another tracing on his final day of research that is equal in its humanity. After close to a year of rigorous experimentation on numerous hospital patients, colleagues, and many an unwitting medical student, Fjord decided to wind down his test. He was ultimately unhappy with the device for a number of reasons, but before he suspended his experiments, on the last day of recording, he recorded a few final subjects, and oddly, for the first time, added an asterisk next to one of the entries. There are a few other unusual facts as well. For only one of the new subjects, he introduced the Roman numeral 1. There's the asterisk and the Roman numeral 1. When for the previous 9 months of studies, he's only ever used the Roman numeral 1 on himself. And additionally, he describes the subject as a healthy woman who was not a patient in the hospital. And this was odd because of all these months of research, he had only recorded a small number of women in general, and they had all been patients at the hospital with a variety of ailments. And in the final odd twist, he only refers to this subject by the initial of her last name, Frau V, or Mrs. V, whereas before he has given the name of each test subject. So it's hard to know the social complexities of testing experimental technology on women in 19th century Germany, and especially when the technology is peering into something as sensitive as the heart and the pulse. But clearly Fjord felt some social obligation of propriety to keep this non-patient's name anonymous. Could this have been from a worry of implying a non-scientific reason for recording her? And why the asterisk, suggesting an importance or singling out when he has never used it before and gives no indications to why he's using it? So if much of literary, musical, and artistic history has been driven by the desire to know the depths of a partner's heart, then on a Wednesday at 3 p.m., September 20th of 1854, science could now add a chapter to this quest. On that final day of recording, he recorded a pulse picture of his wife, Pauline Fjord, becoming the first human to gaze upon his partner's pulse, and hence indirectly her heartbeat, as movement in real time, all while it's being traced by a single human hair and the residue of a candle flame. And Fjord has left no personal reflections behind to describe this day or that he was even aware of what a poetic milestone this was, but the subtleties suggest he was very aware. All we do have is the matter-of-factness of the descriptive language of science. Frau V, age 30, healthy, heart rate 93, 122 pulses with very small effects of breathing. So as descriptions of a partner or a loved one goes, it's certainly lacking any poetic sense of awareness or desire to impress. But rare is the poet who can charge a Roman numeral and an asterisk with as much meaning and tenderness as Fjord did on this final day of experiments. Clearly the scientist, and as I think he seems to have allowed, the partner in him, briefly paused to find some way to recognize this moment. The asterisk and reappearance of the Roman numeral 1, again, seemingly having no other purpose than to acknowledge this private gesture. To trace yourself is one thing, to trace your partner is another. And I'd like to play for you now what Frau Fjord's pulse sounded like on that forgotten poetic milestone when a new form of intimacy was revealed to the world. This is not on the greatest speakers, and I've built it up so much, and I want it to be as impactful, but it is the rhythm. We even can, through Patrick and I's research, we can even mimic the actual rhythm because we know her pulse rate, of course. Fjord wanted to scientifically solve the difficult problem of giving visual form to the ceaseless movement of life in our bodies generated by a beating heart. And although he did not state it this way, nor was it even considered a worthy pursuit of science for many years to come, he had opened the door to the possibility of understanding the physical basis of love and all emotional experience through the most symbolically charged vessel in our bodies. So by quantifying and visually recording the pulse, we now had an indirect window into the heart's behavior. And just as Fjord hoped there would be a diagnostic value in deciphering disease and illness in these pulse waves, maybe one day we could expect even more. Did distinct emotional states register as a unique visual signature in the tracings, for example, and could we expect to decipher it? And in this final unintentionally poetic gesture, the numbers Fjord wrote under Frau Fjord's tracing to mark off each 10 beats as they quickly rushed by and keep some order to them, take on a heightened meaning. Fjord and his wife could never have known it at the time, but they had initiated a sequence of events that set a clock in motion that 123 years later would find its ultimate ambition and the hope Anne and Carl placed in the recordings of her own heartbeat and brainwaves, now speeding into interstellar space. So I will transition and hand it over to Frank to elaborate on some of those thoughts. Thank you so much.
Let's see, which microphone am I supposed to be using? Let me turn on this one. All right, that better? Wonderful. So I am going to provide the scientific counterpoint here. Of course, what Dario's contemplations of heartbeats was partially in his presentation, but what I really was responding to was his look at sound over time. And of course, in astronomy, we don't do very much with sound. So, of course, I said, well, let's take a look at light over time. But when you look at it, and my presentation will hopefully make this clear, you can't just do light and time. You have to also involve space. So I gave it the contemplations of light, space, and time. So the first thing I'm going to talk about is what I call the nanoscale experience. And I'm going to hold up for you a piece of wire that I have cut to be approximately 11.8 inches long. This is my proxy for a nanosecond. And I'll explain just what I mean by that. So nano means 1 part in a billion, 1/billionth. Okay, so a nanosecond is, as you see here, 1/billionth of a second. Right? Very, very short time. Count 1001. A billion nanoseconds passes by every second. Right? And when we talk about light, light moves at a very, 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 very fast speed. The speed of light is 186,000 miles per second. So it's sort of the opposite end, where you're moving extremely fast. Now, if you think about it, how far does light move in 1 nanosecond? And you might expect the answer is 11.8 inches. This distance right here is the distance light can travel in 1 nanosecond, 11.8 inches. If you just divide 186,000 miles by a billion, that's what you get. So the reason why I'm introducing this is if we want to experience light, could we understand it better by looking at it on the nanoscale? Could we experience it nanosecond by nanosecond? So here's a little experiment for you. We're going to start with a dark room. And in this dark room, we have a very special light bulb. This is a light bulb that we can turn on and off on a nanosecond scale. Right? We're going to be able to flip it on and off within a nanosecond. Right? And so we have our darkened room, and then we turn on our light bulb, and it flashes on and flashes off. And that light pulse then starts to propagate across the room. If you experience light on a nanosecond scale, it can only travel almost a foot every second. So you would actually be able to see that light pulse travel across the room and very slowly illuminate the wall of the room so that you can see the structure of what's in the room. Now, what I'm trying to get across here is that as that light pulse travels across the room, each point in space is illuminated only at a specific point in time. The connection between light, space, and time is inherent in the propagation of light. So if I play this as a movie, you can watch this, and you can see the propagation of the light across the room. And you can build up your mental picture of what that room looks like. And if you were watching, you can see that it is a picture of an art gallery, shall we say, with framed Hubble images in it. Sort of suitable for tonight. The point is that this is what astronomers do in looking at the universe. Now, of course, we're not looking at it on a nanoscale. We're looking at it on a megascale, on the macro scale, the largest scale of all. And so we don't need light to shrink down to the nanoscale. We don't need to look at it on a nanoscale. But to give you the idea of how we do this, we then look at it on the overall scale, and that the space and time and light are intertwined. And that is what I call the cosmic time warp. Because we here on Earth will look out into the universe. And if we look to see the moon is more than 186,000 miles away. So that the light from the moon will take more than a second to reach us. Matter of fact, it takes about 1.2 seconds for light to reach us. And those of us who are old enough to remember the Apollo era, if we remember the astronauts on the moon talking with NASA Houston, there was always that delay in the conversation. And it's not because the astronauts had to think, oh my gosh, what am I going to say? No, it was the light travel time of Houston's message going to the moon and their response coming back from the moon that put in a built-in almost 2.5-second delay in all that conversation. If we look a little further into space, our sun, and by the way, if you think this should be yellow, you've been lied to. The sun is not yellow. This is the correct color of the sun. The sun is 500 light seconds away. It takes 500 seconds for light from the sun to reach us, so we see the sun as it was more than 8 minutes ago. The sun is, of course, the nearest star, and it's the brightest star in the daytime sky, but we have a look at stars out there in the nighttime sky. In the lower left, where is this? Okay, in the lower, whoops, there we go. These are the stars of Orion, the constellation Orion. The lower left, this is the star Sirius, brightest star in the nighttime sky. It is 8 light years away, meaning we see the light from it as it was 8 years ago. I like to refer to this as the star for those who do not like the current presidential administration. If anyone's there on Sirius, the light from Earth takes 8 years to get there. The election of President Obama for the very first time has not reached Sirius. So, or any president who can only serve 2 terms, 8 years is long enough that a different president is what is in the knowledge of Sirius. The stars here in Orion, a lot of them, especially here, the Orion Nebula there, 1,500 light years away. We're seeing that as it was 1,500 years ago. Moving on from stars to galaxies, this is the largest, the nearest large galaxy, the Andromeda Galaxy, 2.5 million light years away. So the light from Andromeda has taken 2.5 million years to reach us. So as Dario has looked at things, that looking out at the distances in time to find the sound recordings, we astronomers do that naturally. Matter of fact, we have to do that by nature of our very physics, in that as we look out into space, we also are looking back into time. Now, up to here, out to the Andromeda Galaxy, it sort of matches with that nanoscale example I gave you, because the room didn't change over the course of the light passing over it. And these objects here, well, you know, galaxies don't change much on million-year timescales. But when we look further into the universe, then we start actually seeing changes. So here are some galaxies out to 3 billion light years away. We're seeing them as they are out to 3 billion years in the past. And you'll notice that they have the somewhat of the standard spiral structure. But if I go further than that, billion-year timescales, galaxies do change. So these galaxies are seen from 3 to 7 billion light years away. We're seeing them as they were 3 to 7 billion years ago. And you can see they have spiral structure, but the spiral structure isn't complete. It isn't as full as the nearby galaxies. And if I go even further than that, 7 to 10 billion light years away, 7 to 10 billion years ago, we can see galaxies that have the cores together, but their spiral structure isn't really well developed. So if these are the adult galaxies, maybe these are the teenage galaxies, and these are the children galaxies. Looking out into space, we look back into time, and we can see the history of galaxy development. That's really cool for astronomy. All right? You know, I talk to professors who teach history, and they would love to be able to look out and see the Battle of Gettysburg, or look a little bit further and to see the Peloponnesian War, or see, you know, the age of the dinosaurs. They can't do that, because even the entire expanse of Earth is much smaller than 1 light second. But we as astronomers have the lucky capability of being able to look out into the universe and see distant things. And our greatest expression of it was taken by Hubble, the Hubble Ultra Deep Field, often called the most important image Hubble has ever taken. And in this one image are 10,000 galaxies spread across the distance of the universe. And not just across the distance, but across the time. And the cool thing about this is that when we see these galaxies, we are looking to see where we came from. Because the most distant galaxies, some of the most distant galaxies, it's hard to keep track of the most distant galaxy, okay? Let's be honest with that. So here are some of the most distant galaxies. And these ones we're seeing, actually I believe this one is about 10 billion light years away. So it's not the 13.2 one, but it will look basically the same, okay? These most distant galaxies are small red dots. They're galaxies that are just beginning to form. And this galaxy here, about 10 billion light years away, if there was anybody in that galaxy today looking at our Milky Way galaxy, they would see the exact same thing, because our Milky Way galaxy 10 billion years ago had just started to form. We're seeing the formation of a galaxy there. If there was somebody on that galaxy today, they would see us. We cannot tell you what that galaxy looks like today, right? The light from that galaxy hasn't had time to reach us. It will take another 10 billion or probably more, because of the expansion of the universe, for that light to see it. So what we are doing with the Hubble Ultra Deep Field, and what we will do with the James Webb Space Telescope, the successor to Hubble, is we will be searching for the first light in the universe. We actually can see, with our telescopes, the very first large agglomerations of stars to form in the universe, the beginnings of galaxies. Hubble can only go so far. You notice these are red dots. They are red because the light has been shifted by cosmological redshift. The expansion of the universe stretches the wavelengths of light that travel across it, shifting them towards the red end of the spectrum and even beyond the red into the infrared. Hubble can see the near infrared. The James Webb Space Telescope will look further into the infrared with the resolution that Hubble has. It will be an infrared telescope with Hubble's resolution and be able to see deeper into the infrared to see these most distant galaxies. And that's one of the promises that we're going to do. But I want to take it one step further, because it is not just the interconnection of light and space and time, but it is also our perception of them that is malleable. So this last section called perceptual reality. And it's based on the special theory of relativity from Einstein. The Baltimore Museum of Art, the BMA, is celebrating its 100th year. You know, it's also celebrating its 100th year. Einstein's general theory of relativity. Now, I'm not going to talk about the general theory of relativity. That was 1915. I'm going to talk about the special theory of relativity, which was 1905. All right? And there are two basic ideas behind it. One is that the speed of light is an absolute. Okay? It's represented by the letter c. If there is such a thing as an absolute fastest speed in the universe. That's tenet one of special theory. And then the second one is that the physics is the same to all observers. Whether the observer is at rest or the observer is in motion, you should measure the same physics. And those two ideas lead to some really cool things. First of all, let me just show you that the mathematics can't be the same. All right? When we talk about non-relativistic motion, if, for example, we've got a train car moving along the tracks at 30 kilometers per hour, and you are walking inside that train car at 2 kilometers per hour, your motion relative to the ground is just simply the sum, or 32 kilometers per hour. Okay? That is the standard, what we call a Galilean transformation. However, that can't possibly work with relativistic motion. If the speed of light is to be an absolute, that cannot possibly work. We can imagine a train moving at 95% of the speed of light, and you are a really fast runner, a really, really fast runner. You're running at 1/10 the speed of light inside it, and you would say that, okay, well, Galilean transformation says the total is 5% greater than the speed of light. Which, if special relativity is to be true, which it is, would be wrong. So the standard mathematics that we use at our normal speeds can't apply. Instead, well, just for those who want to know, the relativistic sum works out like this, and you end up where 10% plus 95% actually only gets you 96%. That's just the math for those who are curious in the audience. There will not be a test on this, okay? So things work slightly differently. And in particular, the complications of this, one of the complications of this is time dilation. That time appears to slow down when measured by a moving observer. So we're going to go through Einstein's thought experiment on this. If we have a mirror and we have a light source, and both of them are moving to the right on this page, right? And the light source sends out a beam of light, it strikes the mirror, and then comes back. And we can measure this distance, and we can measure the time in order to calculate the speed of light. So we're going to get that speed of light by measuring the time it takes from when it leaves to get it back and measuring the distance. That's version 1. Version 2 is, well, what if that light source, you are in the frame of reference where you are moving with that mirror and that light source. In the first one, you were at rest and the light source was moving past you. Second one, you're moving along with them. Well, you simply see the light go up to the mirror and back. That's all you see. Again, you measure the distance, you measure the time, you calculate the speed of light. But take a look at the two of them together. When you are stationary, you are going to measure a much longer distance. And so in order to get the same speed of light, you'll have to measure a longer time. Or if you are moving, you measure a shorter distance, and therefore you must measure a shorter time. This is the time dilation effect. In different frames of reference, you're going to measure time differently. The time will slow down when you are measured by the moving observer. And how many of you saw the movie Interstellar? Okay? This was one of the fundamental plot devices in Interstellar. Now, did they do it perfectly correctly? No, they did not. But at least they got the spirit of it correct. That those on the travel to interstellar space and back were going to have a different experience of time. Matter of fact, they would experience less time than those back on Earth. So,
they solved it for love.
Of course, love conquers all right? Except not in relativity, not in the equations of relativity, but at least in the movies. So let me just give you an example here. Travel to Proxima Centauri at 99% the speed of light would take 4.26 years. But the time dilation for this trip, what we call the Lorentz factor, is 7. So that the pilot would only age about 7 months on the way to Proxima Centauri. If you would like to travel into the future, you can. You have to leave everybody else behind in the past. You can't get back to the past, but you can travel into the future by traveling at relativistic speeds. Now, I talked about the connection of light, space, and time. So if time changes when you move, we also have space changing, which is called length contraction. The length of an object will appear shorter when measured by a moving observer. And of course, that means just the length in the direction of your motion. So for example, if a spaceship buzzed past a football field and tried to measure the length of that 100-yard football field, they would measure it as only being 14 yards long. Again, moving at this 99% of the speed of light. All right? This follows in a same sort of thought experiment. I don't have time to go through it tonight. That gives you the time dilation that you get the change in the length. And the crowd would also measure the spaceship to be only 1/7 as long as the pilot thinks, which leads me to my relativistic diet tip for today. If you move fast, other people think that you are thinner. Now, these are great thought experiments, but I wanted to give you one practical example of how we actually observe this. So a proton, a cosmic ray, comes into Earth's atmosphere and strikes an atom. It produces a pion, which then produces a muon. We're going to forget the physics of that. But it produces a particle called a muon, which we can observe on the surface of Earth. Now, here's the thing. Muons decay in about 2 milliseconds. Okay? They decay, they become the gamma rays in about 2 milliseconds. The time to go from where it's created in the atmosphere to the ground is approximately 40 milliseconds, which means 20 decay times, which means we should observe essentially no muons on the ground. But we do observe muons on the ground. Matter of fact, we observe about 1/4 of the muons as we measure high in the atmosphere. What is going on here? From the muon's point of view, it is traveling at 99.94% of the speed of light. It has a Lorentz factor of almost 10, and so instead of actually experiencing 40 milliseconds, it only experiences 4 milliseconds of time. The muons do decay, but they only experience 2 decay times worth of time instead of 20 decay times. Us sitting still measure 40 milliseconds. From its own point of view, the muon only experiences 4 milliseconds, and therefore 1/2 times 1/2 gets to 1/4. We measure about 1/4 of the muons here as we measure up here. A very practical example of time dilation in action that we can actually measure. So this is going to lead me to my final question. Does light exist? Because at the speed of light, time dilation goes infinite, time drops to a standstill. A photon moving at the speed of light does not experience time from its own point of view. And if you think about it, at the speed of light, lengths contract all the way to 0. The photon, from its own point of view, doesn't experience space either. The moment of creation of a photon and the moment of absorption of that same photon are the same moment to that photon. And if it travels from this side of the room to that side of the room, or from that side of the universe to the other side of the universe, it doesn't matter to the photon, it experiences it. We, standing still with our stationary point of view, we see these photons, but from their own point of view, the photon of light doesn't experience time or space. That's a cool concept to think about. All right, so I violated my own rule that I did so many words and pictures and other things that I'm going to finish off with a gorgeous picture. When I thought, here we are presenting to an art audience, I had to think of what do I think of as the really cool art images. And one of them's out in the back hallway there, the Carina Nebula. That's a fantastic image. This one, which actually ties in because it was taken by Voyager, of the Great Red Spot. And you can see all of these wonderful swirls here that look artistic. That's hydrodynamics. That's nature's drawing in the arts, and the swirls and the eddies and the vortices around the Great Red Spot. Thank you for your attention. Okay, so it's 9:15. We've got time for some questions to work on this. So, Dario, you want to come up and we'll do some questions?
Okay.
Sure, as you wish. Yes. Okay. Where's there? All right. So we have questions from the audience here. Yes, in the center there.
You said the muon moves at 99.94%.
Something like that. I don't
Why
remember.
is it not 100?
Huh?
Why is it not 100?
Because the muon has mass, very small mass. The photon does not have mass and can move at the speed of light. Anything with mass cannot move at the speed of light. So it moves close to the speed of light. I might be quoting that number wrong. That's just coming off the top of my head. It's like 99.4 or 99.94. I can't remember.
And when you say it doesn't experience time and space, can that relate at all to the phenomenon of entanglement?
It's a phenomenon of what?
Entanglement?
Quantum entanglement. I'd have to think about that, yeah. I don't think it has much to do with that, because quantum entanglement is on the production of the two oppositely directed items, and that when you observe it here, that you are trying to say that you can predict the outcome elsewhere from that.
Right, but that it's instantaneous.
That's instantaneous. That's instantaneous from our point of view, not from the photon's point of view.
Okay.
So that's where the difference would come in.
Right.
Got a question down front here.
Dario, you talked about the history of sound recording of some type, especially dealing with human art. So if you think about the history, the way history has been recorded over years, it's mostly in storytelling until somebody figured out how to write it down. And that storytelling continued with the same sounds that were there those many years ago. Have you ever looked at where do we go when we go back, and the beginning of storytelling?
Yes, but I'm still focused on that storyteller's, the particular texture of his voice or her voice, whoever was speaking it, that the experience of understanding it as a real-time experience, we're going to hit a wall that we just can't get past. For example, a great analogy I like to use is, think of reading a transcript of Patsy Cline's performance and then hearing Patsy Cline's performance. The gap is so huge that they don't even seem like they belong in the same world. But I think it's related to what you're saying, because for most of recorded history, the transcript of the storyteller would have been passed down, and the next generation would have to understand it through the transcript, so on and so on. Never as the lived embodiment of emotion in the particular textures of a wave that only she was capable of, or any great singer. That, to me, is one of these sadnesses of the people who are interested in understanding where we came from, like you are, and the discrepancy between what you get to, how far back you get to look every day, and as the sound researchers, we're going to keep hitting a wall, which is why I think artists can contribute here, because I think I can come in and ask some weird questions that maybe allow us to work around some of these problems, which I'd love to show you one. I don't know if I hope I'm answering you. So I have looked at, let's say, descriptions of a great Greek storyteller. You know, I've read that, but I'm still reading it, and I still have to use my imagination to understand it rather than experiencing it as a lived sound experience. Does that make sense?
Well, what about imitation?
Imitation, but again, we're still going to hit that wall of, did the imitator get recorded? At some point, we don't have access to the real-time experience. My sound waves are gone before they hit the back of that wall, and every second of our sound lives in general, unless we're recording, it's just gone. And I find this one of the beautiful sadnesses of life on a sound level, that this fleetingness is hardwired into our sensory experience of sound, which maybe why I'm so sensitive to it. I don't know. But I feel like working with people like Patrick, I can help ask them new questions about, have you thought about this as a sound? That are weird workarounds in the way Fjord found a workaround. So I hope I'm answering you. I have thought about them, but you understand what I'm saying? Like we're still going to hit that wall, which for most recorded history has been 1877 until Patrick and his colleagues came along. But think about this. He pushed the line in the sand back 17 years. That's it. Hubble pushes back billions routinely. And as Frank's saying, oh my God, I hope I'm alive the day you released a photo saying this is the first star that ever flickered on. Literally, the let there be light will change. The whole concept will change for so many people. But to build off what you're saying, and so we can wrap up a little, I would love to just show you one thing that I'm currently working on. Frank, do you mind?
Go ahead. Great.
Because this is one of the weird new questions I've been pondering with Patrick about new workarounds to could we inch back a little more? And you have to go with me. I'm being very creative here. Not everybody will go with it. But the one device I showed you, as with most science, everybody's tinkering, trying to find some new way to record. There's a beautiful history of inventions that just didn't go anywhere. But the one we're most focused on right now is this incredible one called the photosphygmograph. And this has the added distinction of bringing photography into the quest of imaging the heart for the first time. And this is quite possibly the earliest, what I'm about to show you is the earliest photograph of the movements of the heart, which this device captured. And what he did that was so ingenious was, this stethoscope head, which he was using as a sound receiver, he would apply to the chest or the pulse, and the vibrations of the sound waves or the movement of the artery would hit the air in here, and it would. This is a column of mercury, like a thermometer, and the mercury would start to bounce up and down in unison with the heartbeat. And he very cleverly made this as a camera obscura. This box would come down, and this is quite also possibly the first use of a photographic plate being moved along, which brings in all kinds of interesting issues with moving film and photography. But this is a photographic plate that's moving along, and this is really beautiful. He would concentrate sunlight into this little receiver here. This is an opening. So the sunlight is hitting that mercury as it's bouncing up and down, and basically making a photograph of the movements of the pulse on the plate. And Charles Ozanam, the added beauty of what he did, which I'm really focusing in on as an artist, is he's one of the, perhaps the first scientist with this new imaging technology to conduct the first sustained study of an aging heart. And it's just nobody had ever done it because they didn't have the technology. So he systematically began recording every person at every age he could find. But these are, could you lower the lights just a little? These are some of the most haunting photographs I've ever seen of these lives. People will never know. A few seconds of their hearts passed by in 1867, and someone, thank God, caught them. And I love meditating on them and thinking of Hubble's imagery that they bring in. Also, this connects in the sense that light is being used. But the question I asked Patrick one day that led us down this road was, who would have been the oldest person to be recorded in this early wave of technology? Meaning, could we find a heart that would have been born in the 18th century? And thank goodness Ozanam was doing his experiments, because in all my research, I've never found a centenarian who was recorded. So as of today, I don't know how much further back we can go. And this is technically a heart that would have been born in 1769. He was recorded just 2 months before he passed away in 1870. And we have a few pulses of a heart that had given him roughly 2.5 billion. And we can glimpse 8 of them towards the end of his life. But this is what I mean. It's not strictly the same as what you're saying, but this is where I think art can help, ask weird, different types of questions. I don't know that anybody would have gone hunting for this unless Patrick and I had this question, and I had just wondered, well, are there other ways to think about this? Think about that. This man would have been a young man during the French Revolution, perhaps served in the war. Neptune was discovered while he was a young man. So these are, if you consider the heart embodying who we are, which I hope I laid out the history of how we do that, then these pulses, that are quickly fading with time, do embody his life and the experiences he would have lived through. So I just think Hubble has done these amazing things about, let's get creative about how we access time. And then I'm just, again, sound's going to hit a wall. I know this is being very playful in my approach, but I don't know how much further back we can go. And we are working on turning this into sound as well currently.
Question.
Can you speak about the correlation between the heartbeat and music, specifically waltz music?
Waltz?
Yes.
Huh. That's the one musical form I'm probably not well versed in enough to speak to.
There is a book, The Secret Power of Music, by David Taine, and he makes a correlation.
Well, I think it's very plausible to suggest that the reason humans, almost universally across time and cultures, one of our rare universal things, we tend to identify who we are in our hearts. That science has changed that quite a bit over the year, argue the heart is a pump, our identity is located in the brain, all that. But just look around for one day in your life, how many times we reference our hearts, or commercials reference hearts, or the new pop song, Kelly Clarkson's new song is about the heartbeat. Everything is hearts, hearts, hearts. And it's not an accident. Why? And I think it's very plausible that that's rooted in the earliest humans understanding that emotions were literally felt in the body by the changing in the heart, which we all still associate today. My heart's beating faster right now. I'm having an emotional reaction. The earliest humans would have had that too. It seems very, very likely music is directly related to that as well. And especially music as one of our early attempts at manipulating our own and others' emotions, which it's a very good tool in doing so. So to me, it is quite likely that the relationship between rhythm and the heartbeat and why it has persisted as a metaphor for so long is because there's something at our core being about it that it goes back to the beginning of art, I would argue. But waltz, I don't know specifically about. Maybe somebody else does.
There's a question in the back corner. I always like to make sure we get the people in the back.
Thanks. I'm wondering, Dario, if you've ever recreated these early technologies that you study, and if potentially using these technologies are even relevant for your artistic practice.
Not the ones I have just shown, but yes, talking about how to remake the silhouette of the side of the portrait of their face could be an interesting thing. So I have not directly made one of these devices, but the logic of the devices is deeply impacting how I'm moving forward in things that I'm making, definitely.
Anything over here?
I should be asking questions but something that interests me about both your work, Dario, as well as the work that comes out of the Hubble is the idea of translation and the extent to which you're reading images and extracting sound from them that is maybe not quite precisely what that sound would have been. The Hubble images, to a certain extent, are constructs. There are choices being made, right, about how colors exactly work on some of those. And so it was just interesting the extent to which translation is a tool in both of your work, and how you deal with producing things that are not quite capturing precisely that thing.
Great, please.
Okay, well, I'll address the Hubble aspect of that first. Because, as I said, Hubble observes in the near infrared. What color is the near infrared? What color is the mid infrared? What color is X-ray? What color is ultraviolet? So what we are observing with Hubble, and matter of fact, a lot of the Hubble images that are in visible light would be the intensity of hydrogen emission, or oxygen emission, or nitrogen emission. So that has a color to it. But when we interpret that into a Hubble image, we need to present it so that it can be understood by the human mind. And not just the public's mind, but even the astronomers themselves, taking that hydrogen, oxygen, and nitrogen image and spreading it across the full color palette is important so that the astronomer can find the various regions and the differences between the various regions. So there is the translation simply in the color. There's also, what I consider astronomy to be is one of the ultimate detective agency things, because we are looking at something that is trillions of miles away, and we are trying to extract the information of what is physically going on there. What are the physical processes that are happening in a place that we can never visit? We can't bring it into the laboratory and slice it and dice it. We have to figure out the physics and the chemistry and all the processes going on by interpreting its light. So there's a lot of what now we have these incredible methods of science to do it, but it is a lot of translation there.
For me, this is a little different because the recording I played, the pulse tracings, we do have to put variables in, but we know the pulse rate, and we know the amplitudes, so we can get very accurate. But the example I showed you of Leon Scott, the folk song, that is really there. You know, it's not. They are their parameters they have to work out because they're dealing with a century-and-a-half-old soot. You know, it's a little pinprick in it, so they have to make some adjustments. But what's so beautiful about that story in particular is, they really didn't know what was going to happen when they played it. And the fact that legible singing comes out of it clearly shows that it is there. So I didn't go into this part of the talk, but there is a distinction between the first recordings made of the heart as sound waves, which would have been directly from the chest wall, and Fjord, who I chose to focus on, which was pulse changes, which was volume change essentially, which we do have to treat differently. But we do have recordings that fall into the Leon Scott category where we're not adding anything. It is there. And I didn't get into that with this. But your bigger point is an important one. Because with work like this, part of being an artist is creative liberties. And I love that. But sometimes work like this requires to be as rigorous as a scientist would. Because I don't want to make it up. It's already available. I just want to reveal the wonder that's there. Which meaning my strategy would be different in how far I allow creative flexibility to come in. And Patrick's much more rigorous on that. So there is a handful of recordings hopefully when this is all done. At this point I have 30 recordings. I would argue all as incredible as I hope you thought that story was. And they are just incredibly lost stories of the heart. And 80% of them would fall into the camp where they're sound, that we're not adding things to it. So there's a distinction to make.
The woman in green cap, did you have a question?
I did, yes. If the first attempt to record sound probably is writing.
Yes.
Okay, and so in your sequence of attempts to record the sounds of the heart, would Hippocrates' writing on the pulse be way in the beginning of the same sequence?
Not in the logic I'm using, in sound as a vibration through the air that was recorded. Written descriptions are the bulk of recorded history about sound. There are centuries worth of descriptions of people debating the sound. And, just the language people have come up with to try to describe heart sounds, which has been, even with Laennec and the stethoscope, there was this wave of, well, how do we convey to each other what we're actually hearing? It sounds like a fish out of water, or slapping of leather. Like this beautiful sequence of words they've come up with. But again, it's still not...
That was technology at the time.
It was, but I want what Frank does, which is I want that sensory experience that only the ear allows. And the fact that we can't access it beyond a certain point, I just find, like I said, this melancholy of hardwired into our sensory experience of the world that I take as a challenge to try to find some way to work around it. And maybe there's something there. I don't know yet, and I'll keep looking for it.
Okay. So we're running late. So one more question there, And John, do we have any questions? Okay. John Maple is checking our web pages and such. Okay, go ahead.
I had a question about the notion of perception in what we're talking about, whether it's the person here on Earth or the telescope in space. It seemed, if I was understanding correctly, that this notion of light and time was relative to the perception and the point in space where the perceiver exists. So my question is, how do you account for that, whether it's in your search for the earliest light? Like, is it not conceivable that that earliest light will have long passed the point of the perceiver? Or if you're talking here on Earth about the perception of length and time being truncated by the perceiver, how do you account for that being inherent to the way in which humans perceive things?
Okay, let me address your first question first. About trying to look for the earliest light. What you have to recognize is that we each exist within our own observable universe. All right? The point is that we're not the center of the universe. We don't believe that there is a center to the entire universe. But inasmuch as we are looking out from our point in space in all directions, we're seeing out into space and back in time equally in every direction around us. And if the universe is only 13.8 billion years old, then from our point in the universe, we can only see a sphere of 13.8 billion light years in radius that is, in fact, centered on us. Now, that's the observable universe as opposed to the entire universe, which can be infinite in size. So our observable universe is centered on us, but that doesn't make us any special because if we were in the Andromeda galaxy, their observable universe is centered on them. Okay? The second point was about the observer having motion that might change their perception. And of course, it is the methods of science to try and remove any observational bias, right? If we recognize that we're always in motion, okay? We're sitting here, I'm sitting still, right? But no, I'm not. The Earth is rotating, so I'm moving at 1,000 kilometers an hour rotating around Earth. Earth is moving at 100,000 kilometers an hour going around the sun. The sun is moving at incredible speeds moving through the galaxy. So there are those frames of reference that we have to take into account. Mark Postman, sitting behind you, has done incredible research on very distant galaxies and looking at distant galaxy clusters. And in understanding the motions of all that, we have to take all of our relative motions into account in order to understand the bulk motions of everything. We have to subtract out what is our frame of reference. I mean, Hubble, when it observes, is moving at 17,500 miles an hour orbiting around Earth. If we don't take out that information that's due solely to that observation, we end up with a biased observation. So removing those observational biases is a very important part of what we do. All right. Last check. Oh, sorry. Go ahead, Dario.
I just wanted to. I just wanted to end on this image. I don't know where we are with it.
Give us a poetic finish.
Yes, I thought just to illustrate my point about what I do sitting in my studio almost every day is looking at these images. And until Patrick and his team came along, this was the oldest recorded music. Did you bring it Do you have the volume up?
give him a big hand, ladies and gentlemen.